So, we in the last class we derived this Lagrangian, which is t minus v for a system, and then we got a series of equations which was of the form ddt of del L del q k dot minus del L del q k equal to 0. So, this means the Lagrangian L in general is a function of q, q dot and time. I should write function of q's, q dots and time. Okay. And this is the general form, I mean this is one form of Lagrange's equation, and there will be n number of such equations. So, the index k actually runs from 1 to n. So, there will be n such equations, okay, n being the number of independent parameters required. So, that is 3n minus k, that means the number of degrees of freedom of the system, I mean available degree of freedom of the system, that is degree of freedom minus constraint, and so we have such k number of equations. Now, we at the end, if you recall, I said something like if Lagrangian does not include one of the coordinate explicitly, that so we have a situation. For example, if I out of this different qk's, if I take one particular qi which is not included in the Lagrangian explicitly. The example I gave was when we wrote the Lagrangian for the central orbit, it did not include theta. Okay. So, theta was included in terms of, I mean theta dot was a part of the Lagrangian, but theta was not explicitly included into the system. So, in that case what happens is, if that particular parameter, in this case q I, is not explicitly involved into the system, explicitly present in the Lagrangian, then this gives you del L del q I is equal to 0 for this particular Lagrangian, I mean for this particular coordinate q I, and this leads to the fact that del L del q I dot is equal to a constant. Okay. And this constant is called, and this quantity del L del q I is corresponding generalized momentum. So, so far we have defined generalized coordinates, we have defined generalized velocities, we have defined generalized forces. So, no harm in defining a new generalized parameter, which is the generalized momentum. Which is equal to this. Okay. So, these terms are essentially your generalized momentum. So, now it makes little more sense, because if this is first, just a minute, pi, yeah, right. So, this is the derivative of the time derivative of the generalized momentum, just like we have in Newtonian mechanics, Newtonian equation of motion, and then we have something which is on the other side. Right. So, exactly, I mean something very similar to what we have in Newtonian mechanics, where we have I mean rather p dot is equal to f, an equation of this form, right. So, it is somehow not very different, and as I am saying it over and over again, that this is just another way of getting this type of equation, which will so Lagrangian, so far what we have learned is another way of getting same set of equation in a slightly different way. Now, we can have situations where we have frictional forces present, or rather dissipative forces present in the system, and sometimes we can have a situation in which we do not know the we cannot really remove the frictional forces a priori. Especially it happens especially for dissipative forces. So, now we will learn how to tackle these two types of situation using this Lagrangian formulation, right. So, the first one we will take up the relatively easy case. I mean both are not very difficult, but we will just out of that two, I would say the first one is this case of dissipative force, case of what you call the viscous damping, for example. So, in viscous damping, what we have seen so far is the force is a function of velocity, the viscous force. If you remember, the viscous drag was written as a general form minus kV. So, minus means it is working opposite to the velocity v, and k is the coefficient of coefficient of the viscous drag, and it is somehow related to the viscous forces present or viscosity of the system and other forces present or other effects related to viscosity that we have seen. Now, this thing, this is a force. So, this is the viscous force or drag force, we can write it as Fd, which is this. Then in Lagrangian, if you see that Lagrangian has a dimension of energy. Now, question is, can we define an energy and define a function which has the dimension of energy? So that can be added to the Lagrangian. The answer is yes. We can, for especially for forces which are or dissipative forces which are dependent on velocity. An example would be, a good example would be viscous force. We can do that. We can write something called a Rayleigh function. Rayleigh function, which has the general form, it is written in using this curly f, okay, equal to half k, or rather kj q dot j, right. So, in this case it will be simply k times v, q dot is equal to, this is a q dot here, okay. So, in the case of viscous drag, it will be simply half k v square, right. So, if we add this with the Lagrangian, we can do that, we can either add it to the Lagrangian, or we can take a derivative or a gradient of this function as a with respect to velocity, which will have this form. And we can put this on the right hand side of this equation. Okay. So, my equation, which was, okay, so keep this generalized momentum in mind, we will come back to this in a moment. Here we are. Okay. So, what we need to do is actually, yeah, so it should be, we have to add this particular term with this equation. So, the total equation we will write as plus del f del q dot is equal to 0. So, I was a bit confused whether I should put a plus sign or a minus sign here. Okay. Now, so this is how we can do, and if we do that, for example, if we are trying to describe the motion of a system falling through a viscous medium, like we did during our initial discussion of motion under resistive medium, we can might as well use this Rayleigh function to get the final equation of motion, and without surprise we will see that we will get back this 2 beta v term, okay, or right, 2 beta v term, which will give you a damping of the velocity, or rather it will be a kv term, simple minus kv term, which will give you a damping of the velocity, right. So, this is one. The second one is, sometimes we face situations where even if we want, we do not have the full knowledge of the constraint forces, or sometimes the constraint forces are also associated with some dissipative force. I mean, certain dissipative forces can be written into this particular form, but there are other types of dissipative forces which cannot be taken into this particular form, but which might be present in the system. One example is the frictional force, for example. Frictional force, okay, let us take an example. A ball or a cylinder is rolling on this platform. Okay. So, if there is no friction, it just comes down, but because there is a frictional force present here, it rolls. Okay. Now, if this rolling takes place, how do we consider how do we include this frictional forces which are causing it to roll into the equation? The answer is we can always find a relation which is somehow which will be something a relation which is very similar to the constraint condition, okay, and we can include that into the Lagrangian. Okay. So, just to give you a brief overview of what I am talking about, in this case, see, if it is rolling without slipping, first of all, how many parameters do we need in order to describe its motion? It is an 1D motion, right. So, in 1D motion, in principle, we can simply take, you know, some reference point and take the distance x of the center of mass, and that should be sufficient. But here we have rolling, and that is when there is no rolling in the system. But when we have rolling in the system, what happens is we also need to define a angular velocity. So, we have to take some reference line, let us say this, we take a line which joins the center of the cylinder with the point of contact, okay, and this is our reference line. We have to take you know, any point on the rim, and we have to monitor this angle, let us call it theta. Okay. So, I mean, it could be this point, it could be any other point, but it has to be a fixed point, and this theta will give you the angular velocity omega in terms of omega equal to theta dot, right. So, when it is rolling, it has an angular velocity, and if the radius is a, radius of the cylinder is a or r, whichever you prefer, let us call it r, then we know that x equal to r theta dot. This relation has to hold. The linear velocity, or rather x dot, is equal to r theta dot. So, the linear velocity and the angular velocity will be connected in terms of an equation. Now, this is a case of non-holonomic constraint. Why it is non-holonomic? Because although we can put it in terms of a differential equation, again, now if I start, you know, writing from here, so I can, this is dx dt and this is r d theta dt. I can might as well get rid of this dt and write it in the differential, I mean the virtual displacement form. This will give you delta x minus r delta theta equal to 0, right. Now, this is some sort of a constraint condition. Whatever may be the motion, this condition has to be fulfilled, and this condition is there because of frictional forces. So, this is some kind of a constraint condition, but for a holonomic system, the constraint equations are in proper form. I mean, this is a derivative form equation, right. So, but for holonomic system, we have seen that constraint equations are given in terms of this type of equation. Please remember that this phi is a function of q1, q2 up to qn, not their derivatives. But here we are getting a relation which is in terms of the derivatives of the coordinate, generalized coordinates x and theta. So, this is not a holonomic constraint, it is a non-holonomic constraint which can still be put in form of an equation. If you recall, during our discussion of the constraints, I said there are certain classes of non-holonomic constraint which can still be put in form of an equation. This is one such example. Another example would be if I take a disk which is rolling on a plane, okay, let us say I do not know, maybe, okay, so this is the plane, let us say my palm is the plane, and then a disk is rotating, I mean rolling on this. Okay. So, what we need to do is we need to define its velocity v, once again there will be a theta, and there will be another angle phi which will be, you know, if my x axis goes like this and y axis goes like this. So, this angle, there should be an angle which gives you the deviation of, you know, the disk plane corresponding to the axis. So, the situation is something like this. Okay. I hope you have noted this already. So, let us say this is my one axis, this is my other axis in that plane, okay, and my disk is rolling in this particular direction. Okay. So, once again we have to take one theta, there has to be a v, velocity v. Okay. So, and there has to be some angle phi, which or phi or psi, whichever, which defines the direction of the disc, which basically defines the direction of the disc. So, this 3, if we can get v which is equal to, let us call it x dot, no vector needed. Okay. So, if we have x dot, theta dot and phi, then we know all about the system. We will know it, but only after we solve the problem completely. Here also we will know what are the values of x and theta, and of course, they are related. Okay. But this will come only after, I mean, we can get an equation with relation between r and theta, and I mean, basically we can get a relation in terms of proper values only after we solve the problem. Here also we can break down the velocity vectors, velocity vector as if v cos theta, okay, which will be the x component of this. Let us say this is x and this is y, and v sin theta will be the y component of it, and I might as well write this as, and this v velocity, v is nothing but, sorry, that's what the mistake was. Okay. So, v is once again, if this is your a, so this is your a, right, sorry, again this will be my phi. Phi is the angle between the plane of the disc and the the direction of the velocity v and the axis, x axis. Okay. So, your v will be a phi dot, right. So, if we replace it with a phi dot, we get two relations. I am sorry, I just mixed up between theta and phi. So, we have a phi dot, sorry, a theta dot, once again sorry. So, we have a theta dot cos phi equal to x dot and a theta dot sin phi equal to y dot. Okay. So, these two relations, once again, it cannot be taken into a non-derivative form unless and until you solve the problem completely, just like we have here. So, these are examples of non-holonomic systems, and sometimes what happens is you cannot really, even if you have an idea of the forces of constraint, you cannot remove them a priori before you solve the problem. It might happen. So, the catch is we can always get to a situation which will lead to which will lead to an additional constraint equation, which has to be taken into account after we write the Lagrangian. Okay. So, it could be a differential form, or even if we have sometime we have a situation where we have a proper holonomic constraint which cannot be removed a priori. Okay. For such situation, we once again have to use the Lagrange's undetermined multiplier. So, the fundamentals are exactly same what we did when we derived Lagrange's equation of first kind. So, I am not repeating that. The trick, so basically from here we have to write d phi equal to 0 equal to sum over d phi equal to 0 equal to del phi del q k delta q k, and this is for the one, if there is one constraint equation, and if there are many constraint equations, for each of them we have to write such equation. Each of them has to be multiplied with a Lagrange's undetermined multiplier, and then a sum has to run over alpha, and each of them has to be added individually to these equations. Okay. So, the final form of equation will be, we will take up examples, do not worry about it, we will take up examples. So, the final form of equation once again will be this equation for one particular parameter, this will be the equation which has to be added up with a term which is sum over alpha lambda alpha del phi alpha del q k, right. Okay. Now, in case of constraint where we have a situation like this, what do? We break it into, for example, here there are two generalized coordinates. Okay. Let us assume that phi is a fixed angle. So, we have two generalized coordinate theta and x, okay. And so, we can bring it to the form that delta x minus a delta theta cos phi equal to 0. Okay. So, this will be the form of one constraint equation. So, there will be two constraint equations, but let us look at it individually. Okay. So, now what we can do is we can write any constraint equation in a general form that it will be sum over k a l k delta q k. In this case, we have two generalized coordinates x and theta. So, correspondingly for x and for theta, we have a x is equal to 1, a theta is equal to minus a cos phi, right. And this is, if you now try to correlate between this and this, it can be, I mean, we can, I can tell you that del phi del x is equal to 1, okay, and del phi del theta is equal to minus a cos phi. Similarly, we can have a second, okay. So, this is phi 1 and phi 1. Similarly, we can write an equation, okay. This is the first equation. So, this is equal to phi 1 and there is a second equation which will give you same set of parameters for phi 2 and we can add them up and get an equation. So, this is right now what we are looking at here is the most general form of Lagrange equation. The first two terms are there for any properly behaving holonomic systems. The third term is there because there is a viscous dissipation which can be written in form of a velocity dependent function called the Rayleigh function, and if there are some additional constraints which cannot be taken into account in terms of or additional dissipative force which cannot be taken into account in terms of this Rayleigh function, then we can write them in form of this part, I mean in form of Lagrange's undetermined multiplier and include them. So, we have in this, using this Lagrangian, we can solve, in principle we can solve any problems. So, now what we are going to do is we will look up some examples and try to see how to use this Lagrangian. We will take up cases where we have Rayleigh function in a system or dissipative system. We will take up a case where we have to use this formalism. So, we will do that, but before that, before we start doing that, I will just want to remind you about one our discussion on symmetric top. So, okay, so I will just erase this for now. If you recall the kinetic energy and potential energy functions, I will just write it directly from this book. So, T was given by half I1 theta dot square plus phi dot square sine square theta plus half I3 psi dot plus phi dot cos theta whole square. That was our T for a symmetric top and our V was mgl minus mgl, no sorry, this is simple mg, L or H, we used L, yeah, cos theta. Okay. So, where phi theta and psi, these are the Euler angles, right. So, now if we form the Lagrangian, what we have to do is we simply have to take, write L here, and we have to take minus mgl cos theta. And these three Euler angles, we can treat them as three generalized coordinates, right. So, if you recall, rigid body dynamics with one point fixed needs 3 degrees of freedom, has 3 degrees of freedom. I mean 3 degrees of freedom are taken away moment we fix one point of it. So, these 3 coordinates can be phi, theta and psi. Now, if we examine this Lagrangian closely, what do we see? We see that out of these 3, phi and psi, these 2 are cyclic coordinates. Cyclic means which is not explicitly present in the Hamiltonian. Theta, we can see that there is sin squared theta here, there is cos theta here, cos theta whole square, there is cos theta here. So, theta at least in more than one places theta is present. But phi, is it present here? No, phi is not present, phi dot is there, phi dot is here. Similarly, for psi, psi dot is here, but there is no trace of psi. So, phi and psi, they are cyclic coordinates. So, in the beginning of the lecture and also in the previous class, the theorem, what I taught you, by going by that, the momentum corresponding to phi and psi will be conserved, right. So, we have p phi will be equal to 0, or rather p phi will be equal to constant. Let us call this constant k, and there will be a p psi equal to a constant, let us call it a. Now, if we try to calculate the momentum, what do we see? Del L del qk dot is the momentum pk. So, going by this, p phi will be equal to, or let us start with p psi, that will be slightly easier. Yeah, p psi will be del L del psi dot, which will be equal to, only one term will contribute because rest of the terms does not have psi dot in it. So, it is a partial derivative. So, only this term will contribute. It will be half I 3, 2 will come, it will be psi dot plus phi dot cos theta, 2 will cancel out, which will have taken equal to A. Is not it the same expression of A which we have derived during our discussion? And it came out, the same constant came out from the third Euler equation, if you recall. Okay. Similarly, so we immediately identify that we have 3 constants during the discussion of symmetric top. One is the total energy, which will be a summation of this and that. Then there was a constant called A, which was exactly that. Okay, there is an I 3 extra here, but we can always do with one constant quantity. I mean, we can slightly manipulate one constant quantity, but at least this part is the same. Now, for the third constant k, it was what was it? It was the z component from looking from space set of axis. It was the z component of the total angular momentum of the symmetric top. Our logic was, because there is no component of torque along the z direction, space z direction, the z direction of space z direction component of the total angular momentum will be constant. So, we took a projection of this total angular momentum in the space z direction and found out there was a constant k. Now, we will do this little trick here, I mean little bit of calculation here. P phi which will be equal to del L del phi dot. Now, which one has phi dot, this one and this one. So, it will be a slightly bigger calculation. If you execute that, let us do it, at least one step we can do. So, this term will not contribute, this term will contribute. So, it will be I1 sin square theta, it will be 2 will cancel out phi dot plus other term, this will contribute. So, it will be I3 psi dot plus phi dot cos theta whole multiplied by a cos theta. Now, you please open your previous lectures, video lectures, or you if you have already taken notes, please check the note. You will find out this is exactly the expression of k we have derived in the class. So, the two conserved quantities which we had, we had our own logic for taking it. One came out from the third Euler equation, the other one was a momentum total angular momentum component along the space z direction. These two are nothing but two conjugate momentums of two Euler angles which will be constant, because the Lagrangian is not explicit function of these Euler angles. So, basically I would say these are two momentums corresponding to two cyclic coordinates of the system. Okay. So, I just wanted to show this to give you an idea of what we have done previously with symmetric top. So, from here what we did essentially, we wrote the total energy instead of L, we wrote the total energy E, we put a plus sign here, right, and then we started manipulating this equation by applying this constraint. So, pure algebraic manipulation to bring that in this particular form. So, we might as well have done this same thing using Lagrangian formulation. That way we would have avoided all the Euler's we did not have to write any of the Euler's equation in order to do that. All we need to do, or we had to do, was to write the energy expression in terms of Euler angles. Anyway, so this is one thing I wanted to show you. The rest will be for the next lecture we will be solving mostly problems. Till then, thank you.